Okay, so we have 100 people, and they have certain friendships between them, which are mutual between pairs of people. And the question is, um, if you can put them into three groups such that in each group there's no friendships, and there's only one way that you can actually do that, um, given that you've already done it. Okay, so given those relationships, there's only one way you can do it. Um, how many? What's the configuration that gives you the least number of friendships? Okay, so um, so there could be lots of ways of having divided into. So it could be lots of different initial conditions with um people being friends with certain people, but given a certain one, there can only be one way in which you can divide them into three groups, such that
Yeah.
within each group no one has a relationship with any other people. And then we want to find out of all the initial configurations, um, sort of which what's the least number of friendships one of them can give. Yeah. Okay, so I'm gonna give a summary. We're not gonna prove everything, but this is just a really quick summary. So obviously we convert this question to graph theory. Okay.
Yeah.
So we represent the people by vertices, like dots, and we represent friendships by edges. Okay, which are connections between the dots. Okay. And so basically we want to partition the dots, 100 dots into three groups for which there are no edges between dots in the same group. Okay. Another way of saying that is you color the dots into three different colors such that no edge goes between two dots of the same color.
Yeah.
Okay. So that's known as a tripartite graph. Okay. And um we want the tripartite graph so that we can't, given the edges where they are, we can't recolor it to make another tripartite graph, right?
Yeah.
That's what uniquely tripartite. Okay. So um, so it's very nice. We claim that the answer is 197 friendships. Yeah, and so we'll give you a construction for 197 friendships. Is you just color one of the vertices black, say, and you color another one red, and then you color the other 98 vertices blue. Yeah.
Yeah.
Okay, and then we have the edges. We make it a complete tripartite graph so that there's like an edge between every possible. Yeah. So every possible edge is there. Okay, and we see that there are exactly 197 edges.
Yeah.
Okay, and it's uniquely by tripartite because, well, if you have a vertex that knows everything, every other person is connected to everything else individually, then they must go by themselves, right?
Yeah.
And so we have two vertices that have to go by themselves. Okay, so the other 98 have to go with each other. Okay, in the third group. So that shows that the answer has to be at most 197. Yeah,
Yeah.
but why is it at least 197? Okay, so this is where came up with a pretty nice solution. So Liam suggested that if it's tripartite, uniquely tripartite, then two of the colors have to be uniquely bipartite.
Yeah.
Okay, and the reason is because if between these two you could recolor them to another bipartite graph, right? Then like with respect to the third part, like the third part doesn't change, right? If you keep the third part the same, they still got no edges between colors between the black vertices. Okay. And And it doesn't matter what edges they have with the red and blue vertices, right? The point is, if the red and blue vertices can be bipartite in a different way, you get something that's tripartite in a different way. Do we need to explain that more?
I mean, I guess it just works.
Yeah. Because the tripart, yeah, like the condition between the black and the red and the blue isn't like the black doesn't care about the red and the blue essentially.
Yeah.
It just worried about whether it's connected to anything within the blacks, right? Because remember we're not really worried about uniquely anymore. We're just proving that there's actually two different tripartite colorings. Yeah, so if some of the blue colors get changed with some of the red colors, yeah, then what do you have to worry about? Well, you have to worry about if the blue ones are connected to other blue ones. You have to worry about if the red ones are connected to other red ones. You have to worry about if the black ones are connected to other black ones, right? So the black ones are still the same, so they're not connected to any black ones. And the red and blue ones are not connected to any of the same color because we're always saying the other thing is a bipartite as well, right? So, yeah, so bipartite is if you color it two different colors such that no edge is between vertices of the same color, yeah? Okay, so then after realizing it was each pair of parts colors have to be uniquely bipartite, basically Alex realized that's equivalent. So is this a well-known lemma or is it you just figured it out? So bipartite, so uniquely bipartite if and only if it's connected. Okay. And okay. And the reason for that is because what does connected mean? Connected means for every two vertices, there's some path of vertices that go there, right? And so without loss of generality, you fix this vertex to be one color. And since every other vertex is connected, like the bipartite condition forces every other vertex to be either the same or a different color based on the parity of the path. You know? So it's at most one coloring. One way of taking two different colors. There could be no ways. Like if the parity changes, there's no ways. But okay, so that proves if it's connected, it's at most one bipartite, at most one coloring, and conversely, if it's disconnected, right? So if it's disconnected, then you might have you have one connected component, yeah?
Yeah.
And you have at least one other connected component, right? Okay. But the thing is, and the coloring is in front of you. It's the red and the blue coloring, right?
Yeah.
So basically, the question is, can you change some of the colors of the vertices and still have a legitimate coloring that makes it bipartite, right? And the answer is yes. So Alex suggested you could just you can just swap red and blue. Yeah.
Yeah.
See, if you swap red and blue, it's still bipartite, right? But you have a different set of red vertices altogether now, and a different set of blue vertices. That makes sense. So before it was like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So before you have the set like 1, 3, 4, 5, 7, 9, 11. That's your set of red vertices, right? But now you have 1, 3, 4, and now it's 6, 8, 10. Right? It's like a different set. So that's not uniquely bipartite, right? So if it's disconnected, it's not uniquely bipartite. If it's connected, it's uniquely bipartite. Therefore, the condition is equivalent. Yeah?
Yeah.
Okay, and then we know that so this is from the basic theory, if a graph is connected, then it has to have at least n minus 1 edges, okay? If there's n vertices, okay?
Yeah.
So if we have three parts, so three colors, say, yeah, and there's I, J, and K vertices, yeah? Then looking at just two of the parts, we have to have I plus J minus 1 edges, right? Between them to make it connected. Because it's uniquely bipartite. And because the edges because the condition of the bipartite says the edges don't go between any of these I vertices, then they have to be different to the edges which make like the I and K components connected. Yeah. And so here we need at least J plus J plus K minus 1 different edges. Yeah.
Yeah.
Okay. But these don't guarantee that. Wait, that's weird. Doesn't this guarantee I and J are connected?
What?
This doesn't guarantee I and K are connected, right?
No.
You need another set of edges.
Yeah.
That sounds weird at the moment because it looks as connected.
Yeah. That makes sense.
Huh?
What?
So it's not the whole thing is connected. It's just I and K individually is connected,
Yeah.
right? So if you just look at the edges between, you just look at I and K and ignore all the things with J. So that ignores all the edges so far, and it has to be connected. So you just have to add new edges, right? So then the edges you have to add over here has to be I plus K minus 1, right? And so if you add them all together, it's pretty cool, right? 2I plus 2J plus 2K minus 3. Yeah? Which is 2n minus 3. And you see that if n is 100, that's 200 minus 3, which is 197. Okay? That's pretty cool. Alright, any questions? It's all good? Yeah. That's it's a very elegant solution.